Okay, so as a final note on today's class, so you've got some summing up on the LP spaces in the lecture notes, so with their the associated norms that we want to use. The reminder that L2 is going to be a very important set for us. All right, so this one, because its norm comes from an inner product, and which you can express like this for real functions. And if ever you've got complex functions, you have, well, it's just very similar to the usual dot product. If you, well, whatever, you have to use not exactly the product of the functions, but the product of one function times the conjugate of the other, right? And the fact that it's a completion of the space of continuous functions. All right, so we said L2 is what is called the Hilbert space. And I like this quotation that I guess I found in Wikipedia. Again, I'm sorry, but this tends to be a very nice synthetic, more or less synthetic pages on math. So it's like a generalization of a Euclidean space to infinite dimensional space. That's the idea. So we're dealing with infinite dimensional spaces, spaces of functions that would not be as well as simple as polynomials, because if you remember what we did last year, working on spaces of polynomials, if you had a finite degree, then you knew that there could be finite dimensional spaces, and that there you could build some basis for them, right? And we're going to do the same thing. We're going to build orthonormal basis for spaces of functions that are potentially, well, infinite dimensional, meaning that you will be able to describe functions by using, well, some functions by using their coordinates in some basis, which would have an infinite number of items in it. Okay, so that's the idea. It extends the methods of vector algebra and calculus to from the finite dimensional Euclidean plane to spaces with finite or infinite number of dimensions. Okay, so Hilbert space is an abstract vector space possessing the structure of an inner product that allows length, again, that's the idea, and angle to be measured. And they are complete. Okay, so you've got a reminder on the Cauchy-Schwarz theorem. All right. Next will be convolutions, but we're going to talk about this more precisely next week, and maybe even do some numerical application of convolutions. So try to have some functional Octave or MATLAB environment that will give us the occasion to work a bit on that. Okay, so that's it for today's class. Just a very, very quick review of some stuffs. Next, so we're going to talk about convolutions. And next thing, we're going to talk about Fourier series. And actually, the Fourier series, so which were first described by Joseph Fourier, a French mathematician. From, well, let's say, was mathematically active at the beginning of the 19th century. That was established by him. This is what we are going to describe as the orthonormal basis for our L2 space. Okay, but well, at the time he discovered that, and that was studying the heat theory. And later on, another chapter we're going to treat later on, and using the Fourier series is going, in particular, is going to be the heat equation. So we're going to study that in details in a few weeks. But whatever. So that was discovered and described by Joseph Fourier, so around 1820. So you can have a look at those Wikipedia pages. Other Wikipedia pages I wanted to give you. Oh yeah, just a quick overlook at the Fourier series. So there are going to be some very simple functions of cosines and sines, which are going to be, so let me find the, okay, some nice views that are going to be used to describe oscillations of functions. And the idea is that if you sum up enough oscillations, then you will be able to describe completely some function, and possibly on a very large, well, on the whole of its domain. Okay, so that's going to be a very nice application of those theories. Okay, again, Fourier series are going to be able to be about finding or proving that some simple functions can be orthonormal basis of our space L2. Okay, so L2 standing for Lebesgue, and here is Lebesgue, so French mathematician from, was born 1875. So, yeah, as we said, he established this theory, or his theory of integration, 1904. Okay, so you can have also look at this page. Next, who are we going to talk about? We're going to talk about Hilbert. Okay, also fascinating guy. So a bit later on. Well, no, not later, about the same time, exactly at the same time. And so the one behind the name Hilbert space or Hilbertian basis, pre-Hilbertian, so that generalization of Euclidean spaces that we saw. Okay, and by the way, the Fourier series are actually called Hilbertian basis. So that you can realize that Fourier had some idea, was not able to prove it very rigorously in any cases, and then the right theory that suited that discovery was established 50 years later. Okay, so that's something that happens sometimes with mathematics. It gets ideas, well, let's say, from the physics side, and then the right theory of mathematics is developed later on. Or the contrary can happen. You can develop some very large mathematical theory and don't see any kind of applications, but then applications are discovered later on, and later on people on the physics side discover it's the right frame for the theories they are trying to establish. Okay, so we have Hilbert, we have at the same time, we have Banach, Stefan Banach. So Hilbert was German, I think. Banach was Polish. Okay, so the School of Mathematics of Wo, I really have no idea how to say that, is this one. It was a very, very famous one at that time of the century. And then, so you've got a lot of things. Maybe you've heard about the Banach-Tarski paradox and things like this. Oh, by the way, Hilbert, another reason why you would have learned about that is the 23 problems. It's problems that he listed 23, actually 24 problems, which some of them are still open problems. Okay, so if you want, and probably you can earn a lot of money if you proved some of these problems. And some have been, some smooth, some have been proved, some have been, oh, maybe let's have a look at this. Hilbert's problem. Okay, so you've got the list over here. So with the year it was solved or not. Some are, the red one are still unresolved. Okay, and some interesting stuffs about this. Let's look at the 18th problem, this one. Okay, you see that this was proved by computer. So computer-assisted proof is also another interesting idea in mathematics. Some people have no problem with that. Some other people say, well, that's not fair, and that shouldn't be a correct mathematical proof, especially when the computer is just acting as oh, so that's a nice one, the sphere packing. Okay, it's how can you pack spheres so that it's the most efficient? Okay, so if you can list all the possibilities, a computer can do that usually. Is that a correct proof? That's still some questions people are debating. Okay, so that was Hilbert. We talked about Banach. And last one, oh, Sobolev. I didn't cite the Sobolev spaces, but Sobolev came a bit later. So he was a Russian mathematician, yeah. And the Sobolev space, let me just finish by giving you this stuff. So Sobolev space, it's going to be, okay, so Hilbert space, we talked about the L2 space. And that was the completion of continuous function. What's happening if you want your function to be even more than continuous, but maybe have its first derivative to be continuous, right? So, or almost everywhere. Well, the completion of so let me find that's again completion of C1. Okay, so L2 was the completion of C0. And what about if I want a completion? I mean, you remember completion means that all sequences have a limit of C1, meaning continuous and with continuous derivatives. So these are going to be the Sobolev spaces, which play also an important role in terms of solving, for instance, partial differential equations or differential equations. So H1 is going to be like F is in L2 and if f is differentiable, Otherwise, we can define some other notion that are close to differentiability. But at that point, let's just say it's f is differentiable. Then f prime is also in L2. Okay, and if f is not differentiable, well, we can find some other ways to go around this problem. Okay, and so you would also have a norm that comes from an inner product, and you can define the inner product in H1. So that's really for your culture, guys. Don't worry about that for the moment. It's just going to be the L2 inner product for the function and the L2 inner product for the derivatives. Okay, so that gives you a Hilbert space of okay, or for infinite dimensional functions. Okay, so hope you're enjoying that. Again, don't worry, it's a lot of very great ideas, but we're going to focus in the exercises on applications, typical applications. Okay, so bye, see you.